Okay, so I shall lecture now. That's obvious. I'm standing in front of you. But the next lecture at 11:45, where I've been lecturing, Dr. Gyan Prakash will lecture. So the course on green tau, the green tau part of the course will start from the next lecture. Okay, very well. So let's continue from where we were yesterday. I just write down the theorem. There'll be some minor differences from what I wrote yesterday, if I remember correctly. In a hurry, I missed a few small facts. So let F be supported F from Z to C. Let me turn off the cell phone before it rings again. Be supported in 1 to n and satisfy 1 is that sigma f of n in Z less than C1n, C1 greater than 1, and of course n is a given integer. So with C1 larger than 1, then secondly, that the LP norm of the Fourier transform of f be less than. So I'll put another constant here, C2 n to the power of p minus 1 for some p greater than or equal to 2. So this, as I said yesterday, in the case of Roth's theorem, this p will be taken to be 2, and you get such a bound immediately from Parseval-Plancherel theorem. But in the case of Green's theorem, this is a non-trivial bound, and p will be taken between 2 and 3. You can fix any p between 2 and 3, say 2.5. And such a bound needs to be proved for the appropriate f that will appear there. Here, of course, f is the characteristic function of the set A that we have been considering. But there it will be slightly different. So there, this needs to be proved as a theorem, and it's what is called the restriction theorem for f, and that will follow from what Satadal exposed yesterday with the large sieve. So yesterday I wrote it in terms of the L infinity norm, saying the L infinity norm of the Fourier transform is less than n, but I prefer to write it in terms of the L1 norm of f here, okay? And then, so suppose this satisfies this. Further, for any eta epsilon with 0 less than eta less than 1 and 0 less than epsilon less than half, let S be the set of T in T such that the Fourier transform is large. Okay, so it's a set of T in T on which the Fourier transform is large, and B S epsilon be the corresponding Bohr set, which is the ends in the dual of T, namely Z, such that the ends are localized in size, so they are not more than epsilon times n, and also they approximately annihilate the elements of S, namely that n times t is less than epsilon for all t in S. So the Bohr set, this is what is called the Bohr set. Yeah, just in case you're wondering, this is not Niels Bohr, but his brother Harald Bohr. Okay, so this has nothing to do with atomic physics or so. Yeah. Okay, so this is a Bohr set, and it approximately consists of those elements in the dual that approximately annihilate a subset of T. Of course, I have not specified, but T is always R mod Z, the circle group I said R mod Z. Okay, and then the conclusion, so under these set of hypotheses, then we then have that the cardinality of the Bohr set Bs epsilon is in fact big, but not terribly big. So epsilon by 4, I probably missed the 4 yesterday, and let me write C3P because I like Star Wars, and times n. Okay, so this is the bound. So this means that this constant depends only on P. Okay, and then you have this. So what this tells you is that the Bohr set is some power of epsilon. So this 1 by eta, because eta is less than 1, this power P is some big thing. So epsilon power that is some very small thing. That multiplied by n. Okay, that many elements at least the Bohr set has. So if your epsilons and etas are balanced enough, you will at least get one element in the Bohr set, and that is the element you will choose to work with to produce this approximate, the B. You will just choose it to be B, and then everything will work. Okay, so that is that. So this is the theorem we prove. And to prove this theorem, we proceed in steps. They're all very standard, simple steps, but nevertheless, for the first time, one will need to go through them a little carefully. So here is the proof. Proof is first one, to prove such a statement is easy or is much more standard when S consists of finitely many points. Okay, so if you have S is a set of alpha 1, alpha 2, alpha R elements of T, this sort of thing is easy to prove, or at least much more standard application of the Dirichlet box principle, and practically the original application of the Dirichlet box principle. So in order to prove it for a set S, which is not necessarily finite, then you have to discretize the set S. So you have to produce a finite set of points inside S with which it is enough to work to get the lower bound for the Bohr set of S itself. So that is what we will do. We will show, so step 1 is discretization. So we will show that there is an integer r greater than or equal to 1 and alpha 1, alpha 2, alpha r in S such that R is less than say some C4 P by eta power P plus 1 in number, and the Bohr set B alpha 1, alpha 2, alpha r epsilon over 2. This Bohr set is contained inside the Bohr set of S epsilon. So we will show that there exists such alpha 1, alpha 2, alpha r. Okay? So then once you have this containment, to get a lower bound for this cardinality, it's enough to bound this cardinality from below, and that's done by the Dirichlet-Box principle. Right. So now how does one prove that there exists such thing? So we let r greater than or equal to 1 be the largest integer such that there is delta space sequence alpha 1, alpha 2, alpha r in S, where delta is equal to eta by 4 pi C1 times n. So where delta is eta by 4 pi C1 n, where C1 is the number that appears here. This is just taken to adjust something. Now what is the meaning of a delta space sequence? This means that alpha I minus alpha j, so this means that is the distance, this alpha I minus alpha j is greater than or equal to delta for all 1 less than I less than j, r where I and j are distinct. Okay, so if you take any two elements of alpha I and of this sequence, they must have a space of at least delta in, and they must be elements of S. So here is your schematic representation of R mod Z, and then suppose that your S is this set, S is like this. You need your alpha 1, alpha 2, alpha R like this. So that these gaps are always greater if you measure with the metric on R mod Z than delta. Okay, so and there will be a largest integer R because this will be some compact subset, and of course you can, there has to be finitely many such R. Okay, so you take such a sequence, then it follows that every alpha in S satisfies alpha minus alpha I is less than or equal to delta for some because otherwise you would have an alpha which is away from all the alpha i's by more than delta, and you can include such an alpha in the sequence and increase the size of the sequence. So because R is the largest integer, and that's the operative phrase here, the largest integer such that this happens, this condition is satisfied just by the contrapositive of that. Also, okay, so this is one observation. Also, now let II be the set of all alpha in T. They may not necessarily lie in S, alpha in T, which satisfy alpha minus alpha I is less than or equal to delta by 4. Okay, this II is defined for each I 1 less than I less than R. Okay, so you define these IIs, they are here. So delta by 4, you notice of course that this S may not contain these IIs, but they are these intervals of delta by 4 length here. Okay, so now these IIs are mutually disjoint. So IIs are the II are mutually disjoint. In fact, if alpha belongs to II intersection ij for j not equal to I, then by the triangle inequality, you have that alpha I minus alpha j is less than or equal to alpha minus alpha I plus the distance alpha minus alpha j. These are less than delta by 4 each, so that's delta by 4 plus delta by 4, which is delta by 2. And this contradicts the choice of the fact that the alpha I, alpha j are delta spaced, right? Contradicting that alpha I minus alpha j is greater than or equal to delta. So you see that these IIs are mutually disjoint. On the other hand, we see that for any alpha in the union of these intervals II, f hat is actually big. The Fourier transform is big. So that's on the one hand. On the other hand, okay, you have that f hat alpha is bigger than, say, eta n by 2 for all alpha belonging to the union of II. For all alpha belonging to the union of II, f hat must be big. Why is that? Because, say, alpha belongs to II for some particular I. Okay? Then you have that f hat alpha in absolute value is greater than or equal to f hat alpha I minus f hat alpha minus f hat alpha I by the triangle inequality, right? And now you see that if you see that f hat alpha I now f hat alpha minus f hat alpha I is less than or equal to, by the triangle inequality, absolute value of f of n, and here E n alpha minus E n alpha I. Okay, n in z. Now this quantity, as I told you from yesterday, a standard inequality, you would say that this is less than 2 pi times n times the alpha minus alpha I. This is less than or equal to that. And then you have the bound for sigma Fn, which is C1n. Therefore, this is less than or equal to C1n. Of course, this little n is less than or equal to n because f is supported here. So C1n times nn times you have the size alpha minus alpha I is delta by 4. So that is eta by pi times my definition of delta had a 4. The denominator, was it 4 pi or pi C1 n 4, let us say. So you get this, and cancelling the n, the C1, and you will get this is less than or equal to eta by 4 pi n, which is certainly less than eta n by 2. Okay, so that's less than eta n by 2. And if you combine with the fact, combining with the fact that this is greater than or equal to eta n, if you combine with this fact, you conclude that because alpha I is belong to S, so f hat alpha I is bigger than this, so you conclude that hence f hat alpha self is bigger than eta n minus eta n by 2, which is eta n by 2. So the Fourier transform is large on this union of intervals, and the number of these intervals is, so now on the one hand, the Fourier transform is large on this interval, so you can use Chebyshev bound to find an upper bound for the measure of this set. Because on this set, the Fourier transform is large, and you know a bound for the LP norm of the Fourier transform. Okay? So because of this, consequently, by the Chebyshev bound, okay, this is not Chebyshev bound in prime number theory, but the fact that you can bound the integral measure of sets on which thing is large, the measure of the union of IR times the value of the function, which is eta n by 2 power p, is less than or equal to the full LP norm, which is less than or equal to n to the power of p minus 1. Okay? By Chebyshev bounds, you have this bound, you have this. On the other hand, the measure, because these intervals II, okay, this must be II, because these intervals II are disjoint, the measure of this is actually the sum of the measures of the intervals II. Okay? And therefore, this measure is, on the other hand, equal to delta by 2 times delta by 4 times R. Also, okay, also 2 times delta by 4, so delta by 2 R is equal to the sum of the measures of II, which is equal to the measure of the union of II, because they are disjoint. Okay, so this gives you a lower bound and an upper bound from here. So you have therefore that hence delta R by 2 times eta n by 2 power p. This is less than or equal to n to the power of p minus minus 1. Yes, so we have this. Now you have to substitute the value of delta, which is chosen to be whatever it is. So therefore, you get here delta is eta by pi c1 n times eta power p times n power p divided by 2 power p is less than or equal to, okay, so it's not less than or equal to n p minus 1, it's less than or equal to a constant which we called C2. So you should be, just because the hypothesis involved the C2, you must put in the C2 from the hypothesis there. So that is less than C2 times NP minus 1. And if you cross multiply everything, there is an R here. You conclude that R is less than or equal to pi C1 C2 2 to the power of p divided by eta to the power of p plus 1 is what you get. Okay, so this depends on p, so you call this C4p by eta to the power of p plus 1. So R is bounded by C4p by eta to the power of p plus 1. So that gives you a bound for R. It tells you that R is bounded by this much. That is one thing. And second thing now is to verify that B, alpha 1, alpha 2, alpha R actually is contained in, I mean the Bohr set corresponding to, now we check that B alpha 1, alpha 2, alpha R epsilon by 2 is contained in BSE epsilon. And that is easy. Indeed, if n belongs to this, you take, let alpha be in S, then n times alpha is less than or equal to n times alpha I plus n times alpha minus alpha I, where you choose the I such that alpha minus alpha I, the distance is less than or equal to delta. Because S, I mean the alpha 1, alpha 2, alpha R have this property that any alpha in S is within delta of one of them. So for a given alpha in S, then there is an alpha I such that alpha minus alpha I is less than or equal to delta. Hence, this is less than or equal. Now, n belongs to this, so that means this is less than epsilon over 2, and this by the triangle inequality is less than n minus alpha I, and therefore this is less than epsilon by 2 plus n times delta. Okay, but n belongs to this Bohr set. In its definition, there is also a size estimate for n, namely that n is less than epsilon capital N by 2. Okay, therefore this is less than or equal hence as n alpha is less than or equal to epsilon by 2 plus here you have epsilon n by 2 times delta, which is eta divided by 4 pi C1 n, and you see that eta is less than 1, this n cancels here, eta is less than 1, So this whole ratio here is less than 1, and therefore this is less than epsilon by 2 plus epsilon by 2, which is epsilon. So that tells you that any n in this set, n times alpha for any alpha in this set is less than or equal to epsilon. Also, because n belongs to this set, and we have used this fact already, we have that n in absolute value is less than epsilon by 2n, which of course is less than epsilon n. So n satisfies both the conditions that are required to belong to this Bohr set, and we are therefore done. Okay? So we have that the cardinality of the Bohr set BSE is bigger than this particular Bohr set. Now, how do I get a lower bound for the size of the Bohr set alpha 1, alpha 2, alpha r? How do we get a lower bound for this Bohr set? Here, one uses a standard argument. So we split to obtain a lower bound for B alpha 1, alpha 2, alpha r times epsilon over 2. So we split TR, that is the torus to the power of this integer r, into half cubes of size of length here, meaning the lengths of the sides, 1 by t so 1 by t, where t you take as 2 by epsilon plus 1. Okay, so this is some number bigger than or equal to 1, and you take this t and you split the torus into intervals of length 1 by t, and then t to the power r you have in boxes. Then you reason that by then, pardon? Half cube meaning not going minus t to t, but just 0 to t. So then by the Dirichlet box principle, we see that there are at least epsilon n by 2 divided by t power r integers in the interval 0 to epsilon n by 2, such that the points n alpha 1, n alpha 2, n alpha r all belong to the same half cube. They all belong to the same half cube. This follows from the box principle. And this means, so you take any one of those points and look at the differences with the remaining, including itself, you will get at least this many integers in the interval minus epsilon n to epsilon n, such that the fraction, the distance, meaning the double distance of n alpha i's is less than or equal to 1 by t. Okay, so this, it follows then that follows that there are at least epsilon n by 2 t to the r integers in minus epsilon n by 2 epsilon n by 2 such that integers k, let us say, such that k alpha I is less than or equal to 1 by t for all I 1 less than I less than r. Okay, so there are at least this many integers. Now it's a matter of estimating this quantity from below, and that is and that would immediately yield the result after you recall that r is bounded above in terms of eta. So here you see that now epsilon n by 2 t to the r is greater than or equal to n by t to the r plus 1, where t is this quantity here, n by t to the r plus 1, and since that is greater than, so this is less than or equal to 4 by epsilon, so that is greater than or equal to epsilon by 4 to the power of r plus 1 times n, and since r plus 1 is bounded above by this C3 whatever by eta to the power p plus 1, this will be bounded below by epsilon by 4 C3 p or C4 p by eta to the power p plus 1 plus 1, and you can take the plus 1 inside because eta is less than 1, so you can write this thing as C4 plus 1 here and then n here. And this C4p plus 1 you can write it as C3p, and that would yield the result as we wrote down. Okay, so you get epsilon power 4 is less than greater than equal to this. Okay, so this gives you an estimate for the Bohr set. This is a very simple but very useful estimate for the lower bound of the cardinality of a Bohr set, and it's used within these Green tau type arguments, a lot of such things quite frequently. This lower bound for the cardinality of the Bohr set. Okay, so it tells you that there are enough almost annihilating characters for a given subset of T, provided that set S is a set on which the Fourier transform of a function is big, and the LP norm of that function is bounded by the appropriate quantity, and similarly the L1 norm and the support. So under these hypotheses, which often appear in practice, you have that there's a lower bound for the cardinality of the Bohr set. Okay, so we are done with that, and now we use this to complete the proof of the theorem of Roth. Was not used, yeah. Somewhere I think you need p minus 1 to be positive, if otherwise you can. So now, in order to complete Roth's theorem from here, you have this bound for the Bohr set. You have to choose your eta and epsilon in the given situation. So let me choose epsilon to be, say, 4 over logarithm of n, and eta to be equal to whatever comes from, so that this bound is so that you have at least one. So you have Bs epsilon is bigger than epsilon by 4 to the power of some constant here, which I have called C3 earlier. I just call it C now, eta to the power p plus 1 times n. And here I already told you in the case of the Roth's theorem, p is taken to be 2 because you only use Plancherel. So this is just eta cube. Okay, so now if epsilon is 4 over n, then I'm going to get here 1 by, so this is greater than equal to, this is equal to say 1 by logarithm of n. And then I have constant by eta cube and n. So if I choose my eta to be equal to, let me say, log n by 2 times the same constant log n to the power of 1/3. If I choose eta to be this, then you see by putting this thing here, the C, maybe I should put the C here. So if I put this, substitute this here, this whole thing is going to simply reduce to n to the power of minus half times n, which is n to the half. And for large enough n, that is strictly bigger than 1. Okay, because eta cube will give me 2c log n by log n. The reciprocal will give me log n by 2c log n. The c will cancel. I get a log n by 2 log n. But this, if I exponentiate, I get an additional log n, which will cancel. And I'll get finally exponential minus log n by half, which gives me n to the minus square root. And therefore, I'm done. So I can choose eta to be 2c log n by log n to the power of 1/3. And epsilon to be this. Once I choose these two, then I know that f hat approximates, so I have constructed, then you take g to be equal to 1 by 3 times the cardinality of the set, the characteristic function of the set 0b 2b. You take g to be this, then you know that g hat t is 1/3 of 1 plus ebt plus e2bt. H should be this. So this convolution with f is g. So the Fourier transform is f hat t. So this f, this is actually 1 by 3 times f of n plus f of n minus b plus f of n minus 2b. So g of n is this, okay? And g hat t is this quantity, and then your f hat minus g hat, f hat minus g hat is less than or equal to the, here you will get epsilon n or eta n, because you're going to get f hat times bt, and if f hat is less than eta times n, then this is just half eta n, or it is less than n epsilon n. And epsilon being smaller than eta, this will give you anyway, everything is less than eta n. Okay, so the difference between the Fourier transform is less than this. I'm just using the fact that either t belongs to S, in which case f hat t is less than or equal to n, and this by the construction b belongs to the Bohr set of S, so this is less than epsilon, so you get epsilon n. That's the second inequality. Or t doesn't belong to S, in which case f hat t is already less than eta n, and this is anyway trivially less than half, so you get half eta n, and so the two combined give you this bound. Okay, and then we saw that the configuration control inequality, where one applied Holder or Cauchy-Schwarz here in the case of p equal to 2, tells us that gamma of f minus gamma of g is less than the L infinity norm of f hat minus g hat by n times n square. In the case of p equal to 2, this is the configuration control inequality, and this gives you, this is less than eta times n square, where eta is that particular expression. Now if you combine all of this, okay, you have this thing. There's only a small glitch in that the support of B of G is in fact contained not necessarily in 1 to n, but it is contained in minus epsilon n to n plus epsilon n. Because G is actually the convolution of f and this thing, and this 2b, okay, so you'll have to put 2 epsilon n, because b can go up to epsilon n. So instead of taking the support of G, we'll let say now T or S be the intersection of the support of G with 1 to n, which would have greater cardinality than the support of G minus 4 times epsilon n. Okay, and the support of G, we know, we have already seen that the support of G is bigger than 3 by 2 times the cardinality of A. So S is bigger than, so the cardinality of S rather, the cardinality S is this thing, yeah, and here this is an inequality for the cardinality of S, hence cardinality of S is bigger than the cardinality of the support minus 4 epsilon n, okay, and we have seen that this is bigger than 2/3, or I mean 3 by 2 times the cardinality of A, hence cardinality of S is greater than or equal to 3 by 2 times the cardinality of A minus 4 epsilon n. And we want this to be greater than, let us say, 4 by 3 times the cardinality of A. Okay, we would like, so that we say that S is at least 4 by 3 times the cardinality of A. So if you subtract for this, we need that the cardinality of A is bigger than doing this subtraction, so that's a 1/6. So 24 times epsilon. Epsilon is 4. 24 4s, it's quickly getting above my abilities. 96 or so, 96 n by log n. So we need that this is bigger than 96 n over log n. Okay? So unless the cardinality of A is bigger than 96 times n over log n, you cannot conclude that cardinality of the S, which is the intersection of A with the support, is bigger than this. But if A is less than 96 n over log n, we are done. Because we have proved that a set of largest cardinality with no 3-term APs actually is small. It's less than 96 n over log n. Okay? So either, thus you have this exception, so which we may, so or else we have cardinality A is less than 96 n over log n, which is very good actually. But anyway, we'll incorporate this into. So now we apply the Varnavedes theorem to S, and we just write down the conclusion. Yeah, A is a subset of 1 to N. Pardon? At most N, that is true. Yeah, but 96N by log N is not huge. No, I mean 96N by log. If you prove this, then you have proved the theorem, because the cardinality of A by N goes to 0 as N goes to infinity, which is what you want to prove. No, please don't think of N as 100 and 200. Think of N as 10 to the power 55 or something like that. I mean, yeah. No, you're an algebraist, so you're thinking of small numbers. We are not even going near them. Okay? Yeah. So let me just finish this now quickly. It's about time this was put to rest. So you have, if I now write down what I did with the Varnavedes lemma after observing that lambda s is greater than Ts, and since S has cardinality more than the cardinality of A, Ts is not 0, Ts is not 0, and therefore Varnavedes lemma gives you that cardinality of S by N minus here you have some Rm plus 1 by M is less than, I'll write this as is less than or equal to Rm plus 1 by M plus M power 4 divided by N square times this lambda of A minus lambda of S plus lambda of S by N square M power 4. Okay, this is what you get. Oh, there's a 4 somewhere, so 4 should be multiplied. You get this from Varnavedes inequality. Now here, things are, cardinality of S is bigger than 4/3 cardinality of A, and cardinality of A by N, so this is just Rn here. Now this difference is what we have bounded as f and g. F is the characteristic function of A. This is 1A, but this is not the characteristic function of the support. This is something which is about 1/3 on the characteristic function. Nevertheless, it's bounded by at most 3 times. I mean, lambda of S would be bounded above by at most 3 times lambda of G. So this is not going to make a difference here, because G is either 1/3 or 2/3 on its support. So you see, you can bound that. So this whole thing is bounded by eta n square. So what this n square cancels with this n square, you get an eta m to the power of 4. So as long as m is such that eta m to the 4 still goes to 0 with n, this term will go to 0. This will go to 0 because the number of 3-term APs in S, I mean, this should be A. In A is trivial, and it's of therefore order n, and if you m power 4 should be less than n. Okay, so m should be chosen such that m power 4 eta goes to 0, m power 4 by n also goes to 0. Now eta is something to the power of 1/3, and you want something to the power of 4 to go slower than that. So you choose m to be, say, 2 times whatever, log n by log n by 2 log n to the power of 1/13 or so. 1/13, then 4 will still be less than 1/3, and then it will cancel. So this quantity will go to 0 with n. And this also will go to 0 with n. Okay? Finally, what happens here? This goes to a limit. We have seen that this ratio has a limit. 1 by m goes to 0. This ratio has a limit, which is what we want to find. So you call that limit, say, alpha. And this goes to the same limit, and you get 4 by 3 alpha is less than or equal to alpha. And the only way out is if alpha is 0. Okay? So that completes the proof of Roth's theorem. So next, we have 2 hours to summarize the proof of Green's theorem. But since many of the preliminaries are covered here, we'll be at an advantage. We can just write down the main steps, and that will be, that would get us the thing. Also, the Sieve things are being, anyway, part of it was done by him, and the other part by Stefan. So we can just quote results and summarize the proof. Right, thanks.